I am Jônatas, and I will be talking about the toolkit, that is the tool that we built for allowing us to run functional pipelines inside SQL. So I am a developer advocate at Timescale. Timescale is the company behind Timescaledb. It's a Postgres extension. It's also open source, and this is a optimization for dealing with time series data. So time series data is massive and scalable data. And then we also have this problem that's like, if we have a lot of data, we also need to have a good tools to analyze this data. And then they just start building the toolkit. So my background is Ruby. I was a Ruby developer for most of my life. And I am also on Java and some other languages, but my main language was Ruby and Shell and Postgres. And I'm running this presentation on a Markdown, so I just built it for this small tool that I'm showing. It's just a Markdown file. I will be sharing it later if anyone would like to check it. So I'm going to just talk about why I'm here, how functions and aggregation works, and how we got inspired on the Postgres design to build our functional pipelines. And then I will show how we implemented it and some examples. So why I'm here, right? So functional programming is so cool. And I was like, wow, this is a functional programming event. I'm going to just try to pitch this idea there, because you are the guys building functional programming. So I'm curious to know who here is a functional programmer developer. Whoa, that's so cool. Yeah, I'm talking to the right people. And the main thing here is like, invite you to take a look and try this out, because we build it, but most of the Postgres users are not really functional guys. So we need to have more people that are familiar with the concepts, and SQL can get complicated really fast. So this is the example that we use to try to explain. So this is like a window function that you just try to use a lag to get the actual element and the previous element, and then you can build a delta between the elements. But this is not very easy. This is not like very easy to do. And instead of this, you can do this type of like functional style with SQL. So this is the thing that we build. So we have this arrow that is nothing else than an operator. So basically, in Postgres, we have this concept of custom type. So you can build, like when you have a table, it's a type, it's a data type, a record type. And then you can also have your custom types. And on the top of your custom types, you can also build custom operators. So if you are familiar with, for example, full text search, they have like at operator, and some like PostGIS, there are their custom operators. So there are custom operators everywhere. And then we thought, why not, right? So we can build it, and that's the idea behind this task. So this is the same example of the previous one, and I will be showing it breaking down piece by piece. So this is the core of our functionality, is have a time vector. So as we are talking about time series, we have a vector which you have like one time dimension plus it's a tuple, and then you also have a value, right? So if I click here, I can run this code, and this is the metadata that is behind this code. So this is like an intermediate step, and this is the type of let's say the intermediate type that we use to build it, right? And when we have this type, we can also just map it to somewhere else. So we can continue using arrow functions on this time vector type. So we call the time vector summary, and then we have this possibility to use this small language that's something that is running behind. So just to clarify, the toolkit, it's written in Rust. So we use a framework named the PGX. That's like a framework to speed up how to build Postgres extensions. And then we use something named code interpreter that is just running these small scripts inside, and you can expose variables from your context to be evaluating something. So if I click here, I will see that now my val is 2 and not 1 because we have an expression and it's compiling. And it's very cool. It's simple, but it can explain the concept. And then we have the problem that we are still in tuple, right? So we need to nest the values, and then we have the real tuple, not like this intermediate state of the objects. And then if we go further, we can do select star from. So this is a very crazy syntax that you need to like wrap it, and then dot star will let you expand and nest, or you can also use a subquery for it, right? So the nest function is like a final function. You have these intermediate functions, and then you have the final function, and that's how it works. And we can also use inline mapping. So for example, if you want to build your custom expression, you can also build it, and then you have the small pieces of of the pipeline. And we build all, let's say, basic math like round, sin, cosine, and all kind of like small math arithmetics inside the library, so you also have access to it. And this is very similar. And we also implemented some stuff to deal with the date time and also intervals, because in Postgres it's very common, you need intervals everywhere. So in this case, I'm just like mapping 1 plus year, and this I here is the identifier that says it's interval. If you're not familiar with this $2 sign is kind of a quote to wrap strings in SQL. So when you need to use the quotes, you can use $sign, and then it's a way to have this type of shortcut. And you can also build filtering, so you can do some very basic filtering. This is just like small examples to clarify the power of this, and then you can customize. So this is an example where you build a SQL function, and then you can just map your data to this SQL function. So you can have ifs and elses and whatever you need there, and build your more complex clauses, and then you can use this map data to just call your function and transform it. So this is all, let's say the intermediate state, and not the transition function, and not the final function. And let's take a look on how it works behind scenes. So we use this PG type of. So this is like a type of, but to know what Postgres types you have behind the scenes. In this case, this is a time vector, and this is a timestamp with time zone with a float 64 as the value of the tuple, right? So for building this, we have this function. I steal it from SQL. So basically, it's like when I say \df on Postgres, so it's like describe functions for me. So I am describing all the functions, but here in the last param, I'm just fetching all the functions that are matching with arguments that are time vector, that is my previous type, right? So I have all these type of functions like a row pipeline, then some row pipeline. So you have a hyperlog log, counter summary, UDD sketch, and we have like 150 different functions, mathematical functions. And what we did was just embed it in this type of pipeline summary and custom types to allow you to also write in this like pipeline style. So, and how aggregates function works, because we are inspired on Postgres. So Postgres aggregation, if you if you want to build aggregation yourself, it's not that hard. You just need to follow this structure. So you have the state function and you have the final function. So in this example, I'm going to show the delta that was the previous example, but just using plain Postgres here, just to clarify how it works behind the scenes. Because in the end, we are just implementing custom aggregates for custom types, and then that's how we map it. So this delta function is just like the function that will allow you to get two elements of one sequence of elements, and then you are appending them, right? And then the final function is, in this case, the delta we cannot be computing, but when we have the final function of delta, we can just traverse the array, and then we go and append the results one by one, and just sum the values here. So this is a very basic thing. I think I haven't compiled it. I need to just click because I'm using a database here and it's not returning anything. And then here is the final, let's say, create aggregation, where you just say to Postgres, well, if I call you delta in the middle of my SQL, you just need to know that this is an aggregation function. So here is the intermediate state function, and then apply the final function as well. So, and let me click here, yes. So here is an example of like just a sales table, and then like you include some elements in the table, and then you can apply the delta. So, and the delta function here is already working with the window function and everything. So you have these delta values that is the difference between the previous values, right? Moving average is another example, very similar, just to have another example here. So I have a moving average, and then if I aggregate, oops, seems I missed clicking here, probably on this one. Yeah, and then I can also run the, oh, it seems like one of my functions is missing. But this is more of the same. I can skip this example. And here is a small video showing how it works. So basically, you call the state function several times, and then when you call the final function, you have this, let's say, transition state that you can reuse. And then the final function will just get the final result and be compiling. So that's not that hard. And we did exactly the same. So if you are interested on this, this is just a link to a blog post that we wrote about how we build this and how we got inspired on Postgres for just like following the same ideas and be compiling it. Yeah, so here I have a few other examples that is just using the toolkit experimental. That is also several of our pipeline functions, they are not stabilized, so we need to just have this experimental extra schema where we put the functions, and if something goes wrong, we can just drop them. And that's why we are looking for feedback. So we need some people to just try these functions and see if they really work and everything is fine, right? And we really need help. So if you like it, if you think that this is a type of thing that you would like to play, this is the repository, Timescaledb is a -toolkit. And we are really looking for like experienced people on functional to do something with it, because like we just have like some basic examples, but we don't know exactly what people can do with it, right? So probably much more than our examples. And here is one example not showing one-time vector, but several. So we have this generate series, and in this case I'm using this generate periodic normal series. I guess I already created this one. And basically, it's just generating some random series. And then I can just have more values to show it, not with a single value. So this is the example that we showed previously. So just like you sort the elements, and then you apply delta, and then you sum the values, and you have some, let's say, volatility or some kind of volatility example, right? And we are building several algorithms for downsampling, because like as we work with a lot of massive data, LTTB is largest tree triangle bucket. So you just try to simplify your time vector, but try to have like the same visual graphic that you would see on a chart with like thousands of points. And that's the main idea. So it will just find the biggest triangles and keep the same consistency. And all the functions, they work well without being on pipelines. We just create these bindings for pipelines to make it fun and cool. But they are like real functions on this domain. And we also implement this tooltext that you can generate like a JSON file directly from it. So for example, here I'm generating encoding and also making it safe for front end. And you can combine it. So I have a small detector here in my front end that if I call some column X and another Y, I can plot it. So for example, here I'm plotting the entire data of my series example. And if I use the toolkit, just like it keeps the same visuals, but with less points. So it's very useful. And we have another downsampling algorithms, but yeah, that's the one that I shows here. And that's it. That's what I want to show you. Yeah, I hope you like it. And here are a few other resources. And if you need it, or if you need to talk to me or anything, my name is Jônatas Paganini. You can find me on JônatasDP on Twitter or Jônatas on GitHub. Yeah.
We have 2 minutes, so it's time for questions.
So first, thank you. This is really fantastic. I mean, switching in the work, during the daily work from writing in functional language to SQL is horrible mental shift, and it's extremely stressful. So I really hope I will have a chance to use it. So I have a nested question, so to speak. So is it production ready? How specific is this to time series analysis? And what's missing to make it suitable for general purpose?
Well, it's not for it's really not connected to our Timescaledb. It works well and very suitable for partitioned data. So if you are using partitions, it will also be able to parallelize the partitions and everything. It's production ready because several of our customers and also the extensions of extension users are using. The experimental is what's not stable. So we have like 20 different functions that are still experimental, but most of them are stable. And we just need feedback to know when the experimental can be stable, right? So more feedback we have, more we will stabilize the functions. Welcome.
One more question.
I don't have a good intuition for performance, as I'm sure most humans don't. But I noticed that on quite a lot of the pure functions that you displayed, the runtime was something like 1/10 of a second, which seems slow. I mean, relative to if you're using Postgres for just a normal query for a table, or if you're running the equivalent pure function in a programming language. Is it that slow? Is it meant to be that slow? What do you think?
Well, I haven't run any benchmark to check how slow it is compared to, let's say, plain SQL processing. What we are doing in most of these functions is just like syntax sugar for Postgres. So we are not really reinventing the wheel, and we are using the engine. My examples here are not really on time series data and not really on massive data. So probably what we see here is just like a local host thing that maybe like is really not optimized. Like this is just prototypes. But we have like clients like ingesting like 1 billion metrics per day, and they use it for dashboarding. So we also have, let's say, other ways to also keep processing data in background. So we have background workers and things that make it fast. But this is like more Timescaledb extension than the toolkit. We saw that toolkit is using Rust, and it seems fast enough, but the PGX, that is the framework behind the scenes, it's also a new framework. So this is like a long-term work. Like we are contributing to PGX as well, but this is really not, let's say, fast as native Postgres, right? So you have the bindings and probably some of the serialization, deserialization between Rust and Postgres could be optimized yet. So, yeah.